Look up at the night sky, and you're seeing an illusion. Oh, the stars are real, the galaxies vast and majestic, but what your eyes perceive is only a tiny fraction of the universe's true substance. For decades, astronomers have been haunted by a ghost, a cosmic phantom hiding in plain sight. We can calculate with astounding precision how much normal, everyday matter should have been forged in the Big Bang. Atoms, protons, neutrons, the stuff you, me, and every star are made of, known collectively as baryons. Yet when we add up everything we can see, from the most brilliant galactic clusters to the faintest wisps of interstellar gas, more than half of it is simply gone. Vanished. This is the missing baryon problem, one of the most persistent and beguiling mysteries in all of modern cosmology. It's as if we've carefully counted all the ingredients for a cosmic cake, only to discover half the flour and sugar have disappeared from the kitchen before baking even began. This isn't a small accounting error. We are talking about an amount of matter so colossal it defies easy comprehension, enough to build trillions upon trillions of new worlds, enough to reshape our understanding of the cosmic web that connects all galaxies. So where did it go? How does half the universe's normal matter simply vanish without a trace? The answer, as it turns out, isn't that the matter is truly gone, but that it's been hiding, woven into the fabric of space in a form so diffuse and elusive that our telescopes, until very recently, simply couldn't perceive it. This is the ultimate cosmic detective story, a puzzle spanning billions of light years, and the search for the solution has taken us on an incredible journey to the very frontiers of astrophysics. And that is the journey we are embarking on together today. We are going to become cosmic detectives, sifting through the evidence, following the trail of clues that scientists have painstakingly uncovered. We won't just be looking at one or two theories. We will explore 25 incredible clues, from the subtle whispers of ancient light to the violent eruptions of distant black holes that are collectively illuminating the shadows. Each clue is a piece of the puzzle, a step closer to solving this grand mystery. So get ready to look at the universe in a completely new way, because we are about to peer into the hidden architecture of the cosmos and uncover the secrets of the missing baryons. Our investigation begins not with a dramatic discovery in deep space, but with a quiet mathematical realization. To understand the scale of the missing baryon problem, we first had to learn how to take a proper inventory of the cosmos. The most reliable ledger we have comes from the very dawn of time, the afterglow of the Big Bang itself, known as the cosmic microwave background, or CMB. This faint all-sky radiation is a fossil, a snapshot of the universe when it was just 380,000 years old. By meticulously studying the intricate patterns in this ancient light, specifically the tiny fluctuations in its temperature, cosmologists can calculate the exact density of normal matter present in that infant universe. It's like having a precise recipe from the original cosmic chef, detailing exactly how much baryonic ingredient, the protons and neutrons that build everything we can touch, was in the primordial mix. Now fast forward nearly 14 billion years. Armed with that original recipe, astronomers turned their telescopes to the universe of today. They began a grand cosmic census, adding up every single baryon they could possibly detect. They counted the dazzling, obvious stuff first, all the stars in all the galaxies, the vast clouds of dust and gas within those galaxies, and the colossal clusters where galaxies congregate. But even when they summed up every last bit of this luminous matter, the numbers were horrifically, inexplicably short. The discrepancy wasn't a small rounding error, it was a chasm. The modern, observable universe appeared to contain only about 40 to 50% of the normal matter that the CMB recipe insisted must exist. Where was the other half? This was the moment the mystery was born. The foundations of cosmology were shaken because the principle of conservation of energy and matter seemed to be violated on a universal scale. If our most fundamental understanding of the Big Bang was correct, then half the atoms in the universe had simply dropped out of sight. This forced a profound shift in perspective. Scientists had to become detectives, acknowledging that the culprit wasn't a flaw in our core theories, but a flaw in our perception. The universe, it seemed, was far more clever at hiding things than we had ever imagined. The missing baryons weren't annihilated or transformed into some exotic, unknown substance. They were simply lurking in a form our technology couldn't easily see. This realization transformed the search from a question of if the matter existed to a question of where and how it was concealed. The hunt was on to find this hidden component of the cosmic web, a component that, by its sheer abundance, forms an essential part of the universe's true structure. If the missing baryons aren't in the stars or the cold gas clouds we're familiar with, then the question becomes, what kind of environment could hide something so perfectly? The most compelling answer points us away from the bright galactic cities and into the vast, dark cosmic countryside, the immense voids between galaxies. It is here, in these seemingly empty deserts, that theorists propose the existence of a phantom atmosphere for the entire cosmic web. They gave it a name that sounds like something from a science fiction novel, the warm-hot intergalactic medium, or the WHIM for short. This isn't a solid object or a cold cloud. It's a form of matter so ethereal and energetic that it challenges our very definition of what a place can be. Imagine the entire space between you and the nearest star, and then between that star and the next galaxy, being filled with an unthinkably thin, superheated gas. This gas is so diffuse that a single coffee mug's worth of it might contain just a handful of atoms, yet it's so hot that those atoms are screaming with energy at temperatures ranging from hundreds of thousands to millions of degrees. This combination of properties is precisely what made the WHIM the perfect hiding spot. Think about how we usually find things in space. We look for the light they emit or block. A cool cloud of hydrogen gas absorbs specific wavelengths of light from distant quasars like a cosmic fingerprint. A hot star blazes with visible and ultraviolet radiation. But the WHIM is caught in a kind of observational blind spot. It's far too hot to emit or absorb the kind of light our optical telescopes are designed to see, and its density is so incredibly low that it barely emits any detectable signal at all. It's the universe's ultimate stealth material, a pervasive fog that has enveloped everything without leaving an obvious trace, which is why our initial cosmic senses came up so short. It was like trying to take a population count by only looking for people standing under streetlights, completely missing the billions of others living in the darkened spaces between them. So, if we can't see this hot, thin gas directly, how do we prove it's actually there? You can't just point a telescope at an empty patch of sky and hope to see a wisp of million-degree fog. This is where our third clue comes into play, a brilliant and subtle piece of cosmic detective work that relies not on seeing the WHIM itself, but on seeing the shadow it casts on the oldest light in the universe. The trick is known as the Sunyaev-Zeldovich effect, and it works like this. The entire cosmos is bathed in the faint, cold glow of the cosmic microwave background, that leftover heat from the Big Bang. As these ancient photons travel across billions of light years to reach our telescopes, some of them pass through the very regions of hot, diffuse gas we suspect are hiding the missing baryons. When a CMB photon happens to fly through a cloud of the WHIM, it has a chance of colliding with one of the super-fast, high-energy electrons that make up that searingly hot gas. In these collisions, the photon gets a significant energy boost, a process physicists call inverse Compton scattering. It's as if the quiet, low-energy photon is being kicked into a higher gear by the frantic, energetic electron. From our perspective here on Earth, this creates a very specific telltale signature imprinted on the CMB. In the direction of a hidden cloud of the WHIM, the cosmic microwave background doesn't look quite right. At the lower frequencies where the CMB is brightest, the cloud creates a slight shadow, a small dimming. But at higher frequencies, that same patch of sky appears slightly brighter than the surrounding CMB. This dual signature, a shadow in one part of the spectrum and a glow in another, is the unique fingerprint of the Sunyaev-Zeldovich effect. It's the undeniable proof that the CMB light has been scrambled by passing through something hot and electrified on its long journey to us. The challenge, of course, is that this signal is incredibly faint. We're not talking about a glaring, obvious distortion. We're looking for a change in temperature so minuscule it's often just a few millionths of a degree. Trying to spot this for a single, isolated filament of the cosmic web is like trying to hear a single person whispering in a roaring stadium. This is where modern astronomy moves from pure observation into the realm of advanced data science. Astronomers can't just look at one spot. They have to employ sophisticated statistical methods on a colossal scale. They gather data from vast surveys of the sky, cataloging the positions of millions of galaxies to map out the large-scale structure of the universe, the cosmic web itself. They know the WHIM should be concentrated in the vast filaments that connect these galactic clusters. Then, they take incredibly sensitive maps of the cosmic microwave background from observatories like the Planck satellite, and they perform a cross-correlation. They essentially stack the CMB data, aligning it with the known locations of thousands of these cosmic web filaments. By combining the data from all these different lines of sight, the impossibly faint individual whispers of the SZ effect begin to add up. The random noise of the universe averages out, and a consistent, coherent signal emerges from the chaos. It's a bit like trying to spot a single specific wave in a stormy ocean. It's impossible. But if you could track the average height of the ocean across thousands of miles, you could clearly detect the presence of a vast, submerged mountain range. This statistical approach gave us our very first indirect but compelling glimpses of the hidden matter. It provided observational evidence that the empty spaces between galaxies were, in fact, filled with a pervasive, superheated plasma. The phantom had left a shadow, and we had finally learned how to see it. But the shadows cast on the cosmic microwave background were just the beginning, a tantalizing hint that pointed us in the right direction. To truly confirm the existence of this cosmic phantom and move from statistical inference to direct observation, we needed a different kind of vision, a way to see the universe not in the cool light of stars, but in the high-energy glare of X-rays. This is where two of humanity's most powerful orbital observatories entered the detective story: NASA Chandra X-ray Observatory and the European Space Agency's XMM Newton. These are not your typical telescopes. They are essentially giant thermos flasks in space, designed to detect the most energetic forms of light, which are completely blocked by our protective atmosphere. They gave us, for the first time, a form of genuine X-ray vision to peer into the superheated heart of the cosmic web. The logic behind using X-rays is beautifully direct. Remember, the WHIM is a gas heated to staggering temperatures between 100,000 and 10 million degrees. At these extremes, the very atoms within the gas are violently agitated. Electrons are stripped away, creating a searing plasma of ions and free-flying electrons. When these particles interact, particularly when a fast-moving electron is deflected by the electric field of an ion, it can release a burst of energy in the form of an X-ray photon. This is the faint, intrinsic glow of the WHIM itself. Catching this glow, however, is one of the most formidable challenges in modern astronomy. The signal is incredibly weak because the gas is so diffuse, and it's spread over vast, filamentary structures that can span tens of millions of light years. It's like trying to spot the heat signature of a single, warm thread from a spider's web that stretched across the entire sky. The breakthrough came not from looking at random empty space, but from targeting the most promising locations predicted by our maps of the cosmic web. Astronomers used these X-ray observatories to stare for exceptionally long periods, sometimes for the equivalent of weeks of total observation time, at the spaces between pairs of massive galaxy clusters that were in the process of merging or were gravitationally connected. These cosmic intersections are where theorists predicted the filaments of the WHIM would be most dense and therefore most likely to reveal themselves. And after years of patient searching, they succeeded. In several landmark studies, teams detected a faint, diffuse X-ray glow emanating from these intercluster bridges. This wasn't the brilliant, concentrated X-ray light from the hot gas within the clusters themselves. This was an ethereal, extended emission that filled the space between them. It was the direct, unmistakable signature of the warm, hot intergalactic medium. For the first time, we weren't just seeing its shadow on other light, we were seeing its own faint, fiery light. One of the most celebrated examples of this was the observation of a filament connecting the two colossal galaxy clusters Able 222 and Able 223. By meticulously analyzing the X-ray data from XMM Newton and combining it with gravitational lensing maps that showed where the mass was concentrated, astronomers could isolate the X-ray emission coming specifically from the filament. They confirmed that the glow was caused by hot, diffuse gas at about 10 million degrees Celsius, and they were even able to make a crude estimate of its mass. This single observation provided some of the most compelling and direct evidence that the theoretical cosmic web was not just a pattern of galaxies, but a physical structure woven from hot, hidden matter. It was a monumental confirmation, akin to a detective finally getting a clear, albeit grainy, photograph of a suspect who had previously been only a name and a description. With each new filament detected by Chandra and XMM Newton, we are not just finding the missing baryons, we are beginning to trace the anatomy of the universe's largest scale structure, drawing the first real maps of the hidden arteries that sustain the cosmic ecosystem. While X-rays gave us a glimpse of the hottest components of the hidden matter, another critical part of the story was unfolding in a different part of the electromagnetic spectrum, one that revealed a slightly cooler but equally vast component of this cosmic phantom. This brings us to our fifth clue, a technique that acts like a cosmic chemical analysis using the universe's own natural lighthouses. The method relies on the unique properties of ultraviolet light and a phenomenon known as absorption lines. Imagine you're a detective trying to identify a particular kind of glass used in a window. You could shine a bright, pure white light through it and analyze the spectrum of the light that comes out the other side. If the glass contains a specific chemical, it will absorb a very precise color from that white light, leaving a dark, narrow line in the otherwise continuous rainbow of the spectrum. This is exactly what astronomers do, but on an intergalactic scale. The brilliant, pure white light source in this case is a quasar, a galaxy with a ferociously bright core powered by a supermassive black hole. These quasars are so luminous they can be seen from the farthest reaches of the universe, their light traveling for billions of years to reach us. As this quasar light journeys across the cosmos, it passes through the various structures of the cosmic web, including the filaments of the warm, hot intergalactic medium. The WHIM isn't just a uniform gas, it contains specific ions, atoms that have been stripped of some of their electrons by the intense heat. Crucially, these ions, like oxygen-5, oxygen-6, and neon-8 are in the perfect state to interact with ultraviolet light. When a photon from the quasar has exactly the right energy to excite one of these ions, it gets absorbed, creating a tiny, dark dip in the quasar's ultraviolet spectrum at a very specific wavelength. Each type of ion creates its own unique set of these absorption lines, a barcode that identifies its presence. Finding these specific barcodes in the light of a distant quasar is direct, incontrovertible proof that the light has passed through a cloud of million-degree gas on its way to Earth. It's like finding the specific fingerprint of the suspect on the windowpane, placing them directly at the scene of the cosmic crime. The beauty of this method is its precision. By measuring the exact wavelength of the absorption line, astronomers can determine not only the composition of the gas but also its distance from us, thanks to the redshift caused by the expansion of the universe. This allows them to build up a three-dimensional map of where these hidden filaments are located. However, there was a major obstacle to reading these cosmic barcodes. Earth's atmosphere is a wonderful shield, but it completely blocks ultraviolet radiation, making it impossible to conduct these observations from the ground. This is where our sixth clue and a remarkable spacecraft entered the story, the Far Ultraviolet Spectroscopic Explorer, or FUSE. Launched by NASA in 1999, FUSE was a specialized observatory designed with one primary goal: to be the universe's ultimate ultraviolet detective. Its mission was to peer into the distant cosmos and capture the high-quality spectra of quasars and other bright objects in the far ultraviolet range, a part of the spectrum that was largely unexplored. For nearly a decade, FUSE stared at hundreds of quasars, collecting their light and meticulously breaking it down into its constituent colors with phenomenal sensitivity. It was specifically tuned to look for the telltale absorption signatures of those key ions like oxygen-6 that are the hallmark of the warm-hot intergalactic gas. The data that streamed back from FUSE was a game-changer. Before FUSE, detections of the WHIM using this method were scarce and uncertain, but FUSE provided a flood of evidence. It didn't just find one or two absorption lines, it found a veritable forest of them. By analyzing multiple lines of sight to different quasars, the FUSE team was able to demonstrate that these filaments of hot gas were not rare anomalies but a pervasive and integral part of the cosmic landscape. One of the mission's most significant achievements was its ability to measure the density and distribution of this gas. By studying how deep the absorption lines were and how they were distributed across different redshifts, scientists could begin to estimate just how much normal matter was tied up in this form. The findings were staggering. The FUSE data suggested that an enormous reservoir of baryons, potentially enough to account for a large portion of the missing matter, was indeed floating in these vast hot filaments. The mission provided the first widespread, direct sampling of the WHIM, moving the search from theoretical prediction to observational certainty. It was as if FUSE had given us a net fine enough to catch the individual particles of this cosmic fog, confirming its existence not just as a shadow or a faint glow, but through the direct chemical signature of its most abundant elements. While FUSE gave us the chemical fingerprints and X-ray observatories captured the faint glow, we still needed a grand, unifying map to understand how all these pieces fit together into a coherent whole. This brings us to the seventh clue in our investigation, a concept so fundamental it redefines our entire mental picture of the cosmos, the cosmic web. Forget the old idea of galaxies scattered randomly through space like lonely islands in a dark ocean. The true architecture of the universe is far more structured and intricate. On the very largest scales, matter is arranged in a breathtakingly vast network, a cosmic spiderweb of staggering proportions. This web is composed of three primary elements. First, there are the dense knots, the galaxy clusters, which are the grand metropolises of the universe where thousands of galaxies swarm together. These clusters are interconnected by long, thread-like filaments, the cosmic highways and bridges that can stretch for hundreds of millions of light years. And surrounding it all are the immense, empty voids, the true deserts of space that are largely devoid of both galaxies and, we once thought, any significant amount of matter. This cosmic web isn't just a beautiful pattern. It's the underlying skeleton of the cosmos, the framework upon which everything is built. And it is precisely within these vast, diffuse filaments that our missing baryons were predicted to make their home. The web isn't just a structure of galaxies, it's a structure of mass, and a significant portion of that mass was hiding in plain sight, woven into the fabric of the filaments themselves. But how do we know the cosmic web is real if we can't see most of it? This is where our eighth and perhaps most crucial clue comes into play, a tool that allows us to run the universe in fast-forward, supercomputer simulations. To solve a cosmic mystery, sometimes you have to build your own universe from scratch. Scientists start with the initial conditions of the Big Bang, a nearly uniform soup of matter and energy, and input all the known laws of physics, most importantly the relentless shaping force of gravity. They program in the precise amount of dark matter, which makes up about 85% of all matter and acts as the cosmic scaffolding, and the exact amount of normal baryonic matter we know exists from the cosmic microwave background. Then they press play and let the simulation run for billions of years of cosmic evolution in a matter of weeks. The results are not just impressive, they are eerily accurate. As the simulation progresses, gravity begins to work its magic. Tiny, random fluctuations in the primordial density of dark matter are amplified over eons. Dark matter, which doesn't interact with light and only feels gravity, collapses first into a delicate, invisible network of filaments and nodes. This dark skeleton then acts as a gravitational trap for the normal baryonic matter. The gas, the protons and neutrons that form stars and planets, is pulled by gravity into the same vast filamentary structure. It flows along the dark matter highways, falling into the gravitational potential wells and heating up to incredible temperatures through shocks and compression as it crashes together at supersonic speeds. These simulations, with names like Illustris and Eagle, don't just predict that a cosmic web should exist. They show us in stunning, dynamic detail exactly what it should look like and where the Baryons should be. They paint a vivid picture of a universe where the bright galaxies we see are just the tip of the iceberg. The simulations confirm that a huge fraction of the normal matter, between 30 and 50%, never makes it into those bright galaxies at all. Instead, it is destined to remain in a diffuse, hot state spread across the immense filaments of the cosmic web. This is the theoretical roadmap for observers. It tells the astronomers with their X-ray and ultraviolet telescopes exactly where to look. The simulations predict the density, temperature, and distribution of the warm-hot intergalactic medium with remarkable precision. They show that the filaments connecting the most massive galaxy clusters should be the easiest to detect, as they are the densest and hottest. They also reveal that cosmic events like galaxy collisions and outbursts from supermassive black holes act as immense pressure cookers, injecting even more energy into these filaments and making them slightly brighter and easier to spot. Without these supercomputer simulations, the search for the missing Baryons would have been a blind, aimless hunt in an impossibly large haystack. The simulations provided the blueprint, transforming a bewildering mystery into a targeted search mission. They gave us the confidence that we weren't just chasing ghosts, but were on the verge of mapping the hidden arteries of the cosmos, the very channels through which the universe built itself. Now, with our map from the simulations and the confirmation from Fuse, the search became more targeted, focusing on the specific atomic elements that would serve as the ultimate tracers of this hot, elusive gas. This brings us to our 9th and 10th clues, which revolve around two particular forms of a very familiar element, oxygen. You might not think of oxygen as a cosmic detective, but in the searing heat of the intergalactic filaments, it becomes a brilliant beacon. Under normal conditions, an oxygen atom has 8 electrons orbiting its nucleus, but when it's bathed in the million-degree temperatures of the WHIM, it undergoes a dramatic transformation. The intense heat violently strips away some of those electrons, leaving behind a charged particle known as an ion. The specific ions that astronomers got most excited about are called O7 and O8. O7 is an oxygen atom that has lost 7 of its 8 electrons, leaving it with just 1. O8 is even more extreme. It has been completely stripped, a bare oxygen nucleus. These highly ionized states are the hallmark of an environment of truly ferocious heat. the kind of heat that only exists in the most energetic places in the universe, like the vast spaces between galaxy clusters. The reason O7 and O8 are such perfect tracers is twofold. First, oxygen is one of the most abundant elements in the universe, forged in the hearts of massive stars and scattered across the cosmos by supernova explosions. So wherever this hot gas exists, there's a good chance it contains a significant amount of oxygen. Second, and more crucially, the specific energy transitions of these ions. The precise amount of energy needed to bump their remaining electron into a higher energy level or to absorb a photon completely occur at very specific wavelengths in the soft X-ray part of the spectrum. This is like each ion having its own unique radio frequency on which it broadcasts. When the light from a distant, brilliant quasar passes through a filament of the WHIM, the O7 and O8 ions in that filament act like a filter, absorbing X-ray photons at their exact signature wavelength. This creates two very specific dark lines in the quasar's otherwise smooth X-ray spectrum. Spotting these lines is the smoking gun. It's the equivalent of a detective finding a suspect's unique DNA at a crime scene. It doesn't just tell you that something was there, it tells you exactly what it was and the extreme conditions it lived in. Finding these cosmic fingerprints, however, is a monumental technical challenge. The absorption lines are incredibly faint, and the X-ray photons from the distant quasars are themselves relatively scarce. This isn't like the rich, detailed spectra we can get from optical telescopes. It's more like trying to discern the fine print on a document by the light of a single, distant candle that's flickering in the wind. It requires exquisitely sensitive X-ray spectrometers, instruments that can spread the faint X-ray light out into its constituent colors with phenomenal precision. Observatories like Chandra and XMM Newton have this capability, but even for them, detecting a clear O7 or O8 line often requires hundreds of hours of dedicated observation time on a single quasar. The signal is so weak that for many years these lines remained more of a theoretical prediction than a common observation. But when they are found, the payoff is immense. Each detection allows astronomers to measure not just the presence of the hot gas, but also its temperature, since the relative strength of the O7 and O8 lines tells you how energetic the environment is, and its distance from us based on how much the expansion of the universe has redshifted the lines from their expected laboratory wavelength. It is through this painstaking line-by-line analysis that we are slowly but surely building a chemical and physical profile of the phantom matter, transforming it from a theoretical concept into a characterized component of our universe. This challenge of faint, individual signals brings us to one of the most powerful and ingenious methods in the modern astronomer's toolkit, a technique that moves beyond the hunt for a single, perfect observation and instead embraces the collective power of many. We group this approach as our 11th and 12th clues, stacking analyzers and statistical detection. The core idea is both simple and brilliant. Imagine you're trying to listen to a radio station that's plagued by static. If you only have a single, quick recording, you might not be able to make out the song at all. But if you record the same station 100 times and then layer all those recordings on top of each other, averaging them together, something remarkable happens. The random, chaotic static being different in each recording starts to cancel itself out. Meanwhile, the consistent, underlying signal of the music, which is the same in every recording, gets reinforced and amplified, emerging clear and strong from the noise. This is precisely what astronomers do in their search for the WHIM. A single absorption line from one quasar or a faint X-ray glow from one filament might be too marginal to claim a definitive discovery. It could just be an instrumental quirk or an unrelated fluctuation. But if you take data from hundreds of different quasars, all shining through different parts of the cosmic web, and you stack their spectra on top of one another, you can tease out the consistent, universal signature of the intervening gas. The process is a masterclass in data science, First, researchers use vast galaxy surveys to map the large-scale structure of the universe, identifying the likely locations of cosmic filaments. Then, they gather archival data from telescopes like Hubble, Fuse, Chandra, and XMM Newton for every known quasar whose line of sight passes through one of these predicted filamentary regions. They don't look at these spectra one by one for a dramatic, obvious line. Instead, they shift each spectrum to a common reference frame, effectively removing the effects of cosmic expansion to line up where the absorption from a specific ion, like oxygen-6, should appear. When they stack them, they aren't looking for a single, deep spike. They are looking for a tiny, consistent dip that appears at the same relative position in thousands of spectra. This dip, which would be invisible in any single dataset, becomes statistically significant when combined with all the others. It's the average whisper of the WHIM heard across the cosmos. This method doesn't give you a detailed picture of any one specific filament, but it provides something arguably more powerful for solving the missing baryon problem. It confirms the pervasive, ubiquitous nature of the hidden gas. It tells us that the WHIM isn't just present in a few special places. It's a universal component, a fundamental part of the interstellar medium that fills the cosmic web everywhere we care to look. The results from these stacking analyses have been nothing short of transformative. They have allowed scientists to move from asking, "Did we detect it here?" to declaring, "This is how much of it there is on average throughout the universe." By measuring the average depth and width of the stacked absorption lines, astronomers can calculate the typical density and temperature of the gas in these filaments. These large-scale statistical studies have been crucial for closing the budget on the missing baryons. They provide a robust population-level measurement that confirms a significant portion of the predicted ordinary matter is indeed in the form of this hot, diffuse plasma, distributed along the cosmic web's invisible scaffolding. It's the difference between finding one fingerprint at a single crime scene and having a comprehensive database that proves a suspect was active across an entire city. This powerful, statistical approach has turned the faintest of cosmic whispers into a confident, collective shout, confirming that the phantom matter is not only real, but is also present in precisely the abundance needed to solve the mystery that started this entire investigation. But there's another, even more dramatic way to weigh this hidden matter, one that uses the most powerful and enigmatic flashes in the universe as our measuring stick. This brings us to clues 13 and 14, which revolve around one of the most exciting discoveries in modern astronomy, fast radio bursts, or FRB. Imagine a cosmic strobe light so powerful that in a mere thousandth of a second, it can release more energy than our sun puts out over several decades. These are FRB's incredibly brief, intensely bright pulses of radio waves that originate from galaxies billions of light years away. For years, their origin was a complete mystery, with theories ranging from colliding neutron stars to alien communication. While we're now fairly certain they are produced by extreme astrophysical objects like highly magnetized neutron stars, their incredible power and vast distances make them far more than just a curiosity. They have become, almost by accident, one of the most precise tools we have for probing the fabric of the cosmos itself. The secret to their utility lies in a concept known as the dispersion measure. Here's how it works. An FRB is not composed of a single pure radio frequency. It's a broadband blast, meaning it contains a whole spectrum of radio waves from lower frequencies to higher ones. As this burst travels across billions of light years of intergalactic space, it doesn't move through a perfect vacuum. It passes through the diffuse sea of free electrons that make up the warm, hot intergalactic medium. Now, when a radio wave encounters a free electron, its speed is ever so slightly altered. Crucially, this effect is frequency dependent. The lower frequency radio waves are slowed down more significantly than the higher frequency waves. It's analogous to how different colors of light are bent by different amounts when passing through a prism, creating a rainbow. But in this case, it's not creating a rainbow, it's creating a time delay. So when that brilliant millisecond flash finally arrives at our radio telescopes here on Earth, we don't receive it as a single, sharp pulse. Instead, the higher frequency waves arrive a fraction of a second before the lower frequency waves. The entire burst is stretched out or dispersed over a short span of time. This stretching is the dispersion measure, and it is a direct and quantifiable record of the burst's journey. By measuring precisely how much the pulse has been spread out, astronomers can calculate the total number of free electrons it encountered along its path from its host galaxy to us. Think of it like running through a crowded room. If you have to weave around people, you'll be slowed down. The more people in the room, the slower your overall time. In the case of an FRB, the people are the free electrons in the WHIM, and the dispersion measure tells us exactly how crowded the cosmic room was that the burst had to pass through. This makes FRBs the ultimate cosmic yardsticks for weighing normal matter. Every single free electron along the line of sight contributes to the dispersion measure, and since these electrons are tied to protons, which make up the bulk of the mass in normal matter, measuring the electrons allows us to directly weigh the baryonic content. It's a beautifully straightforward method. A larger dispersion measure means more electrons, which means more baryonic mass between us and the burst. The real power emerges when we know the distance to the FRB, which we can now determine by identifying the host galaxy with optical telescopes. Once we know the distance, we can compare the total amount of matter we'd expect to find along that vast distance with the amount we actually measure via the dispersion. Early results using this technique have been stunning. When astronomers analyze the dispersion measures of FRBs from different distances, they find a clear and consistent amount of missing matter that is not accounted for by the visible galaxies and gas clouds. This extra material, revealed only by the delayed radio pulses, matches the predicted density of the WHIM perfectly. Each FRB is like a single, brilliant flash of lightning in a dark landscape, illuminating for a split second the entire terrain between us and the storm, allowing us to finally see the hidden contours of the cosmic web and confirm that the phantom matter is indeed there, accounting for the weight we knew was missing all along. For a long time, astronomers had a powerful, traditional tool for mapping the invisible structure of the universe, a method that predates the hunt for the WHIM but set the stage for it. This is the Lyman Alpha Forest, a name that sounds like something from an enchanted realm, and in a way it is. It's a magical window into the cosmic web, but one with a critical blind spot. The technique relies on the most abundant element in the universe, hydrogen. When a distant quasar shines its brilliant light across space, the neutral hydrogen atoms it passes through act like tiny filters. These atoms are very particular. They love to absorb light at one specific wavelength in the far ultraviolet part of the spectrum, known as the Lyman alpha line. Now, because the universe is expanding, each cloud of hydrogen gas is at a slightly different distance from us. This means the light absorbed from each cloud is stretched or redshifted by a different amount. When astronomers take the spectrum of a single quasar, they don't see just one absorption line. They see hundreds, even thousands of them, each at a slightly different wavelength, creating a dense, intricate pattern of dark lines against the bright, continuous backdrop of the quasar's light. This is the forest, a breathtaking record of the distribution of neutral hydrogen clouds along that one specific line of sight, a single core sample drilled through the vast expanse of the cosmic web. This forest gave us our first three-dimensional maps of the large-scale structure of the universe, long before we could see galaxies at similar distances. It revealed that space is not empty but is filled with a complex, interconnected network of gaseous filaments, exactly as the simulations predicted. For decades, this was the gold standard for studying the intergalactic medium. By surveying the Lyman alpha forest in the light of many quasars, astronomers could essentially create a tomographic map of the cosmos, charting the vast, sponge-like distribution of matter. It was a revolutionary discovery that confirmed the web-like nature of the universe. However, this powerful tool had a fundamental and frustrating limitation, one that ultimately defined the very nature of the missing baryon problem. The Lyman alpha forest is exquisitely sensitive to neutral hydrogen gas that is relatively cool, perhaps 10,000 to 100,000 degrees. But as we've learned, the majority of the missing baryons are not in this cool, neutral state. They are in the warm, hot intergalactic medium, a plasma so hot that the hydrogen atoms are violently stripped of their electrons. In this ionized state, hydrogen has no electron left to absorb that characteristic Lyman alpha light. It becomes invisible to this traditional method. The Lyman alpha forest, for all its beauty and utility, was only showing us the cool, dense tips of the icebergs floating in the cosmic ocean, while the vast, submerged bulk, the hot, ionized water itself, remained completely hidden from view. This stark contrast between what the forest revealed and what it concealed was a pivotal moment in cosmology. It drew a clear line in the sand, defining the search parameters for the missing matter. It wasn't that our maps were wrong, they were just profoundly incomplete. The cosmic web wasn't just made of cool, neutral hydrogen clouds. It was a multi-phase medium, a cosmic ecosystem with components at vastly different temperatures. The Lyman alpha forest was an incredible tool for studying the cool component, but it was utterly blind to the hot, dominant component that simulations insisted contained most of the mass. This realization is what forced the development of all the new methods we've discussed: the X-ray observations, the ultraviolet surveys with fuse, the statistical stacking analyzers, and the use of fast radio bursts. The limitations of the Lyman alpha forest didn't invalidate it. Instead, they highlighted the complexity of the universe and pushed astrophysics to develop a more complete and nuanced toolkit. We learned that to see the true cosmos, we couldn't rely on a single type of vision. We needed to combine the optical view of galaxies, the ultraviolet view of the cool gas, the X-ray view of the hot gas, and the radio view of the electron haze to finally assemble a complete picture of where the universe stores its ordinary matter. The forest showed us the trees, but it took a whole new suite of astronomical instruments to reveal the entire hidden ecosystem. So we've seen how single quasars act like cosmic lighthouses, their light revealing the shadows of hidden matter along one narrow path. But what if you could use two lighthouses shining through the same patch of cosmic fog from slightly different angles? This brings us to a sophisticated and powerful technique using closely spaced pairs of quasars. When two quasars happen to lie very near each other in the sky, from our perspective, their light travels along two almost parallel paths across billions of light years. Think of it like a doctor taking two X-ray images of a patient from slightly different positions to create a three-dimensional CT scan. In cosmology, this method is known as tomographic mapping, and it allows us to do something extraordinary: reconstruct the three-dimensional architecture of the warm, hot intergalactic medium. Here's how it works in practice. Astronomers use massive sky surveys to identify these rare and precious cosmic duos, quasar pairs separated by just a few arc minutes on the sky. For each quasar, they obtain a high-resolution spectrum, revealing the dense forest of absorption lines created by hydrogen and other elements in the intervening gas. Now the magic happens in the comparison. If the WHIM were simply a collection of small, isolated gas clouds randomly scattered through space, then the absorption patterns in the two quasar spectra would be completely different. Each line of sight would pierce through a separate set of unrelated clouds. But if the gas is arranged in the vast, continuous filaments predicted by the cosmic web model, then the two closely spaced sightlines should show strongly correlated absorption. They would both slice through the same gigantic structure, just at slightly different points. By analyzing the similarities and differences between these two absorption forests, astronomers can perform a feat of cosmic triangulation. They can measure the physical size and geometry of the absorbing structure. If a specific absorption feature appears at the same cosmic distance in both spectra, it means the cloud responsible must be larger than the separation between the two lines of sight at that distance, which could be 1,000,000 light-years or more. This is a direct way to distinguish between a small, puffy cloud and a massive, sheet-like filament. The data from these quasar pairs has provided some of the most compelling observational evidence that the absorbing structures are indeed enormous, coherent, and continuous, exactly matching the predictions for the filaments of the cosmic web. It moves us from simply knowing that the gas is there to understanding its shape and extent on the largest scales. This tomographic approach transforms our understanding from a two-dimensional sketch into a rich, three-dimensional model. Instead of just a single core sample, we get a cross-sectional view. By studying many such quasar pairs probing different parts of the universe, astronomers can begin to stitch together a full tomographic map of the hidden matter distribution. They can see how filaments branch and connect, measure their density gradients, and observe how they funnel material toward the massive galaxy clusters at their intersections. It's a technique that finally allows us to trace the ghostly anatomy of the cosmic web in 3 dimensions, confirming that the phantom matter isn't just a diffuse haze but is structured into the very backbone of the cosmos, the vast channels through which galaxies form and evolve. But the story of the missing Baryons isn't just about vast, empty intergalactic space. It's also a tale of cosmic expulsion, of matter being violently thrown out of its galactic home and into the great beyond. This brings us to clues 19 and 20, which focus on the dynamic environments right around galaxies themselves. For a long time, we pictured galaxies as relatively isolated islands holding onto their stars and gas. But we now know they are more like active volcanoes, constantly spewing material out into their surroundings through tremendous outbursts of energy. This process is known as galactic feedback, and it's driven by 2 of the most powerful engines in the universe, supernova and active galactic nuclei. When massive stars reach the end of their lives and explode as supernova, they do more than just create dazzling stellar fireworks. They generate colossal shock waves that rip through their host galaxy, heating surrounding gas to immense temperatures and pushing it outward at thousands of kilometers per second. On an even grander scale, at the heart of most large galaxies lies a supermassive black hole. When this black hole is actively feeding on surrounding material, it becomes an active galactic nucleus, or AN, launching jets of plasma and radiation that can punch clear through the galaxy's gas reservoir. This feedback acts as a cosmic regulator. It prevents too much gas from cooling down and forming new stars too quickly, which is why we don't see galaxies with exponentially more stars than they actually have. But this regulatory process has a major side effect. It continuously pumps baryons out of the galactic disk and into the much larger region surrounding the galaxy, known as the circumgalactic medium. This isn't a gentle leak, it's a systematic ejection, a primary mechanism for seeding the intergalactic void with the very hot, diffuse gas we've been searching for. So, where does all this ejected material go? It doesn't just vanish into the deep intergalactic medium immediately. A significant portion of it gets caught in the galaxy's gravitational embrace, forming an immense hot atmosphere that extends far beyond the familiar spiral arms or elliptical glow. This is our 20th clue, the discovery that galaxies are surrounded by massive, extended halos of warm, hot gas. Think of it as a galaxy's ghostly, gaseous corona, a halo so vast it can be 10 times larger than the visible galaxy itself and contain as much normal matter as all the stars within the galaxy combined. For decades, these halos were theoretical predictions, but observations have now confirmed their existence. The Chandra and XMM Newton X-ray observatories have detected the faint, diffuse glow of million-degree gas enveloping many large galaxies, including our own Milky Way. Furthermore, the Hubble Space Telescope and instruments like the Cosmic Origin Spectrograph have found the telltale ultraviolet absorption lines of highly ionized oxygen and neon in the light of distant quasars, lines that are created when the quasar's light passes through the halo of a foreground galaxy. These observations paint a consistent picture, a massive reservoir of hot, tenuous gas held loosely by a galaxy's gravity, acting as a crucial interface between the dense galactic interior and the even more diffuse WHIM of the cosmic web. This circumgalactic medium is not a placid reservoir, it's a dynamic cycling system. Gas is constantly being injected into it by galactic feedback, and it's also constantly cooling and raining back down onto the galaxy to fuel new generations of stars in a vast billion-year cycle of cosmic respiration. The discovery of these massive halos was a paradigm shift. It showed us that a galaxy is not just the bright part we see in photographs. Its true extent and a huge portion of its ordinary mass exists in this invisible hot corona, a halo that had been hiding in plain sight all along and now accounts for another substantial chunk of the universe's once missing baryons. While our existing X-ray observatories like Chandra and XMM Newton acted as powerful cosmic spotlights, revealing individual filaments through painstaking, targeted observations, a new instrument has taken to the skies with an entirely different ambition: to conduct a grand, systematic census of the entire hot universe. This is our 21st clue, the groundbreaking work of the eROSITA X-ray telescope. Launched in 2019 as the main instrument on the Russian-German Spectre RG satellite, eROSITA was designed with one primary, sweeping goal: to perform the most sensitive all-sky survey in the history of X-ray astronomy. Imagine the difference between using a high-powered flashlight to examine specific, interesting rocks in a dark cavern, and then switching on the overhead lights to see the entire cavern system, its grand arches, hidden tunnels, and connecting passages all at once. That is the transformative leap that eROSITA represents. Over its first 4 years, it has scanned the entire sky not just once, but 8 times, building up an incredibly deep and detailed map of the high-energy cosmos. This monumental dataset is not just a collection of pretty pictures. It is a quantitative inventory of the hot, energetic phenomena across the universe, and it is providing the most compelling large-scale evidence yet for the hidden Baryons. The true power of eROSITA in this cosmic hunt lies in its unique combination of a large field of view and superb sensitivity. While Chandra provides exquisitely sharp images of small areas, eROSITA can rapidly cover vast swaths of the sky, making it the perfect tool for finding the faint, extended emission that characterizes the warm, hot intergalactic medium. Its all-sky map is essentially a heat map of the universe's most energetic structures. On this map, the brilliant, point-like flashes of active black holes and neutron stars are visible, but so too is a faint, pervasive glow that traces the underlying cosmic web. This is the diffuse X-ray background, and eROSITA detailed measurements are allowing scientists to dissect it with unprecedented precision. They can now separate the emission from distant, unresolved point sources from the genuine, smooth glow coming from the truly diffuse hot gas in the filaments connecting galaxy clusters. It is within this faint, background hum that the majority of the missing baryons have been hiding, and eROSITA is giving us the first clear, all-sky picture of their distribution. One of the mission's most significant contributions has been its ability to detect and characterize the hot gas in the outskirts of galaxy clusters and in the filaments between them on a statistical level that was previously impossible. By stacking the eROSITA data for thousands of known galaxy clusters and their interconnecting regions, astronomers have been able to measure the average properties of this gas with remarkable accuracy. They can now determine its typical density and temperature, and crucially, they can begin to weigh it. Specific findings from these analyses are staggering. They suggest that the warm hot gas in these large-scale structures accounts for a massive portion of the predicted baryons. In fact, when combined with the baryons locked in stars and the cooler gas within galaxies, the numbers are finally starting to add up. The eRosita survey is providing the robust observational data needed to close the baryon budget, strongly indicating that the mystery of the missing matter is at long last being solved. The phantom is not only being seen but is also being counted, and its total mass aligns beautifully with the predictions from the cosmic microwave background. This represents a monumental convergence of theory and observation, a triumph of modern cosmology that was made possible by this one-of-a-kind telescope's panoramic vision. Yet as we piece together this map of hot gas and glowing filaments, we must confront a profound and essential truth about our universe. The very architecture we've been tracing, the cosmic web itself, is not built by the normal matter we are made of. Its blueprint is drawn by an invisible hand. This brings us to perhaps the most fundamental clue of all, one that underpins the entire structure of the cosmos, the indispensable, indirect role of dark matter. While dark matter itself is not baryonic and doesn't contribute to the missing matter problem directly, it is the master sculptor that carved out the hiding places for those missing baryons in the first place. Think of it like this: if the universe is a grand, magnificent cathedral, then the glowing galaxies and the hot gas of the WHIM are the stained glass, the ornate decorations, and the gilded surfaces. But dark matter is the unseen flying buttresses, the massive stone pillars, and the hidden foundation that holds the entire structure aloft. Without this dark scaffolding, the beautiful and intricate design would simply collapse into a formless heap. This gravitational influence is not a subtle effect. It is the dominant force shaping the cosmos on the largest scales. In the early universe after the Big Bang, dark matter began to clump together first. Because it doesn't interact with light or normal matter through any force except gravity, it was free to start collapsing under its own weight long before ordinary atoms could. Tiny, random ripples in the density of this dark material were amplified over billions of years, growing into a vast, interconnected network of dark matter filaments and halos. This process created a gravitational landscape of immense hills and valleys, a cosmic terrain that would dictate the flow of everything else. When the normal, baryonic matter, the protons and neutrons that form stars and planets, finally entered the picture, it had no choice but to follow this pre-existing dark matter topography. The hot gas flowing into this dark skeleton gained tremendous energy, heated by shocking collisions as it was funneled at high speeds into the dark matter filaments and nodes. This is why the WHIM exists in those specific, vast structures connecting galaxy clusters. It is tracing the underlying, invisible mass of the dark matter web. The dark matter created the gravitational potential wells, and the baryonic matter simply fell into them, heating up in the process and creating the very environment that made it so difficult for us to see. This relationship completely reframes the missing baryon problem. It shows us that the reason we couldn't find half the universe's normal matter for so long is precisely because dark matter had organized it into a form that was perfectly engineered to evade our detection. If the cosmos were made only of the normal matter we understand, gravity would not have been strong enough to pull matter into such a vast, filamentary web in the relatively short time since the Big Bang. The baryons would be far more uniformly distributed, a thin, even soup without significant large-scale structure. In such a universe, the missing baryon problem might not even exist, or it would be an entirely different kind of mystery. Instead, the relentless collective gravity of dark matter forced the baryons into a specific configuration, one that is incredibly diffuse and hot, spread across millions of light-years of empty space. So, in a very real sense, dark matter is the reason the baryons went missing in the first place, and understanding its role is the key to knowing where to look for them. This highlights a beautiful and deep interconnectedness in cosmology. You cannot truly understand one component of the universe, like the location of normal matter, without understanding the influence of the other, more dominant component, which is dark matter. Solving one mystery often requires grappling with another, showing us that the cosmos operates as a single, complex, and deeply intertwined system. While our tools for directly detecting the WHIM have grown more sophisticated, an entirely different kind of measurement has been working in the background, providing a rock-solid baseline against which all our discoveries must be measured. This is the work of the Baryon Oscillation Spectroscopic Survey, or BOSS, an ambitious project that is part of the legendary Sloan Digital Sky Survey. BOSS didn't go hunting for faint glows or subtle absorption lines. Its power lies in creating the most detailed three-dimensional map of the universe ever made, a cosmic cartography project of staggering scale. By meticulously measuring the precise distances to over 1 million galaxies and quasars, it allowed scientists to trace the large-scale structure of the cosmos with unprecedented fidelity. And etched into that structure, like a fossilized imprint from the dawn of time, is a specific, measurable pattern known as Baryon acoustic oscillations. To understand what these oscillations are, we need to travel back to the universe's first few 100,000 years. At this time, the cosmos was a seething, opaque plasma, a hot soup of photons, electrons, and atomic nuclei. In this dense fluid, gravity was constantly trying to pull matter together into clumps, while the intense pressure of the trapped light, the radiation, was pushing it back out, creating a continuous tug of war. This conflict set up rhythmic, spherical sound waves that rippled outward through the primordial plasma, much like the spreading circular waves from a pebble dropped in a pond. These were acoustic waves, with the baryons, the normal matter, effectively surfing the crests and troughs. This churning continued until the universe cooled enough for atoms to form, a moment known as recombination. At that instant, the photons suddenly decoupled from the matter and streamed freely across space, becoming the cosmic microwave background we observe today. The baryons, however, were frozen in place, left stranded at the precise distance that the sound waves had traveled. This created a fundamental, standard ruler in the cosmos, a characteristic scale about 500 million light-years across, imprinted on the distribution of matter. BOSS' genius was in detecting this frozen echo in the modern universe. By mapping the positions of millions of galaxies, its scientists could look for a subtle statistical preference for galaxies to be separated by this specific 500 million light-year distance. It's the same principle as hearing an echo in a canyon. The time delay tells you the canyon's width. In cosmology, the echo is the overabundance of galaxy pairs at this specific separation, which reveals the size of the standard ruler. Because we know the true physical size of this ruler from our understanding of the early universe, we can use its apparent size in the sky to measure cosmic distances with phenomenal accuracy. This allows us to track the expansion history of the universe and, crucially for our mystery, to make an incredibly precise count of the total baryon density. The strength of the baryon acoustic oscillation signal depends directly on how much normal matter was present in the early universe to participate in those primordial sound waves. BOSS provided a definitive, independent ledger of the universe's original baryon budget, a number that aligns perfectly with the one derived from the cosmic microwave background. It is the control in our cosmic experiment, the unshakable number that tells us beyond any doubt exactly how much normal matter we should be looking for. This makes BOSS the ultimate arbiter in the missing baryon hunt. Every filament of hot gas detected by Chandra, every absorption line found by Fuse, and every electron cloud weighed by a fast radio burst contributes to a running total. BOSS provides the grand total we are trying to reach. Its measurements are so precise that they don't just tell us baryons are missing, they tell us exactly how many are still unaccounted for at any given time. As observations from other methods have steadily improved, the gap between what BOSS says must exist and what we can actually see has been narrowing dramatically. This convergence is one of the great success stories of modern cosmology. It means our various, independent paths of investigation mapping galaxies, probing ancient sound waves, and directly sensing hot gas are all leading us to the same coherent conclusion. The phantom matter is being found piece by piece, and the master ledger from BOSS is the proof that we are finally balancing the universe's books. But our ability to see the cosmic web in its full glory is on the verge of a quantum leap, pushing beyond the statistical maps and faint whispers into an era of direct, vivid observation. This final clue catapults us into the near future, where a new generation of astronomical giants is being built, instruments with such staggering power that they promise to not just find the missing Baryons, but to study their intricate dynamics in exquisite detail. Leading this charge are two behemoths, the James Webb Space Telescope, already revolutionizing infrared astronomy from its vantage point a million miles from Earth, and the ground-based extremely large telescope currently under construction in the high deserts of Chile. While JWST peers deep into the infrared universe, the ELT, with its colossal 39-meter primary mirror, a mosaic of nearly 800 hexagonal segments, will gather more than 10 times the light of the largest optical telescopes today. This isn't a simple upgrade, it's a fundamental shift in capability. The combined power of these observatories will allow us to attack the mystery of the warm-hot intergalactic medium on multiple fronts simultaneously, with a sensitivity and resolution that borders on the unimaginable. One of the most immediate impacts will be in the study of the cosmic barcodes, the absorption lines imprinted on the light of distant quasars. Current telescopes can detect these lines, but often they are just marginal detections, their true shapes and depths blurred by noise and limited spectral resolution. The ELT, equipped with ultra-stable, high-resolution spectrographs, will change this completely. It will be able to dissect the light from incredibly faint quasars at the edge of the observable universe, revealing the absorption forests with a clarity we've never had before. We won't just see a single dip for a specific ion, we'll see the complex velocity structure within individual filaments. Imagine being able to listen to a symphony and not only hear the melody but also distinguish the individual instruments and even the breath of the musicians. The ELT's data will show us how the gas is moving within these cosmic tendrils, whether it's flowing smoothly toward a galaxy cluster or turbulent from a recent galactic outburst. This will transform the WHIM from a static, hidden reservoir into a dynamic, flowing component of the cosmic ecosystem, allowing us to understand its role in the continuous cycle of galactic birth and death. Furthermore, the sheer light-gathering power of these new telescopes will unlock a treasure trove of fainter, more distant quasars. Every new quasar we discover acts as another flashlight beam shone through the cosmic web, and with thousands more beams at our disposal, our tomographic maps will achieve a resolution that was previously science fiction. We will move from confirming the existence of a few large filaments to weaving a detailed, three-dimensional tapestry of the entire web structure across vast cosmic volumes. This will allow astronomers to perform a complete, large-scale inventory of the intergalactic medium, measuring the density and temperature of the gas in filaments of different sizes and at different epochs in cosmic history. We will be able to answer questions like, how has the amount of hot gas in the web changed over time? How does the efficiency of galactic feedback in ejecting baryons vary with the mass of a galaxy? The answers to these questions are written in the subtle patterns of absorption in quasar spectra, and the ELT and JWST will be the first instruments with the visual acuity to read that fine print. Perhaps the most breathtaking possibility, however, is the potential for direct imaging. While seeing the faint, diffuse glow of a single, isolated filament remains an immense challenge, the enhanced capabilities of these telescopes make it a plausible goal for the first time. By combining the infrared sensitivity of JWST to see through cosmic dust with the phenomenal resolution of the ELT to pick out minute details, astronomers may be able to target the brightest and densest predicted filaments. They won't appear as glowing, solid ropes in the sky, but through advanced image processing and by combining observations across multiple wavelengths, we could create maps where the ethereal structure of the web becomes visually apparent, superimposed on the blackness of space. It would be the ultimate confirmation, a direct portrait of the phantom architecture we have been inferring for decades. This isn't just about closing a ledger, it's about opening a new field of study. With these tools, the hunt for the missing Baryons will transition into a golden age of exploration, where we can finally begin to understand the physics governing the largest and most mysterious component of our universe's ordinary matter, tracing the hidden rivers that have shaped cosmic evolution since the beginning of time. This brings us to the ultimate question, the moment of truth for our cosmic investigation. After following these 25 intricate clues across the electromagnetic spectrum, from the subtle shadows on ancient light to the delayed whispers of fast radio bursts, where do we stand? Are we any closer to declaring this case closed? The answer is both exhilarating and humbling, a testament to how far we've come while revealing just how much finer detail remains. By synthesizing the evidence from every front, the faint X-ray glow mapped by Erecita, the chemical fingerprints of ionized oxygen found by Fuse and Chandra, and the electron sensors conducted by fast radio bursts, cosmologists have been able to construct a new, comprehensive inventory of the cosmos. The current best estimates are nothing short of revolutionary. It appears that we have now located and accounted for somewhere between 70 and 80% of the universe's missing normal matter. The grand majority of this long-lost material is indeed residing in the warm, hot intergalactic medium, the superheated plasma that threads the vast filaments of the cosmic web and halos galaxies in massive gaseous coronas. The phantom, after decades of evasion, has finally been cornered. This is a monumental achievement. Think of it as a massive accounting reconciliation. For years, our ledger showed a catastrophic shortfall. Now, by carefully adding in all these previously invisible assets, the hot gas in the filaments, the circumgalactic halos, the diffuse plasma revealed by stacking analyzers, the books are getting much closer to balancing. The convergence is stunningly consistent. The dispersion measures from FRB's point to a specific density of free electrons in intergalactic space. The X-ray emission and absorption line studies provide independent measurements of the density and temperature of the gas containing those electrons. And the theoretical framework from supercomputer simulations, which predicted this very configuration, provides the scaffolding that makes sense of it all. These aren't just separate lines of evidence, they are different instruments in an orchestra, all finally playing the same symphony. They confirm that the cosmic web is not a theoretical fantasy but a physical reality, and that it contains a colossal reservoir of ordinary matter in exactly the form we least expected. Yet, a discrepancy remains. If our predictions from the cosmic microwave background and Baryon acoustic oscillations tell us 100% of the Baryons should be there, and we've found around 70 to 80%, what constitutes the final 20 to 30%? This remaining gap is not a sign of failure, but rather a beacon guiding the next generation of discovery. There are several compelling explanations for this final disparity. One possibility is that our current observations are still not quite sensitive enough to detect the very faintest and most diffuse components of the WHIM. The cosmic web has a wide range of densities, and the gas in the most tenuous regions, particularly deep within the great cosmic voids, may be so incredibly thin that it barely emits or absorbs any signal at all, even for our most powerful instruments. It's the difference between being able to see a dense fog and struggling to perceive a barely noticeable haze on a humid day. The very most elusive Baryons could be hiding in this ultra-diffuse state, requiring even more sensitive telescopes or more sophisticated statistical techniques to uncover. Another fascinating possibility involves the very nature of the circumgalactic medium. We know galaxies are surrounded by these massive halos of hot gas, but accurately weighing them is notoriously difficult. Their edges are fuzzy and they blend almost imperceptibly into the general intergalactic medium. It is entirely plausible that these halos contain even more mass than our current estimates suggest, making up a significant portion of the remaining missing fraction. Furthermore, some theorists speculate that a portion of the baryons could be locked in yet another hard-to-detect form, such as in compact, dark matter-dominated dwarf galaxies or in vast populations of rogue planets and stars that have been flung out of their home galaxies into the emptiness of intergalactic space. While these wouldn't account for a huge percentage individually, collectively they could chip away at the remaining gap. The final steps in closing the cosmic ledger are therefore the most challenging, demanding that we push our technology and our models to their absolute limits to probe the faintest echoes of matter in the most remote and unassuming corners of the universe. The hunt is no longer for a phantom, but for its faintest ghost. So, after this incredible detective story spanning billions of light years and countless observations, you might be wondering, why does this all matter? Is it just about balancing a cosmic ledger, making the numbers add up for the sake of neat accounting? The truth is, solving the missing baryon problem reaches far beyond a simple checkmark in a textbook. It strikes at the very heart of our understanding of the cosmos, acting as a critical test for the entire standard model of cosmology. Think of this model as the fundamental operating system for the universe, a set of rules and ingredients that includes dark energy, dark matter, and the ordinary baryonic matter we're made of. For decades, this model made a very specific prediction that a certain amount of normal matter must exist. The fact that we couldn't find half of it was a glaring, persistent anomaly. If we had never found those hidden baryons, it would have meant there was a catastrophic flaw in our basic understanding of physics. It would be like a master chef following a recipe perfectly, only to end up with half a cake. You'd be forced to question everything: the recipe, the ingredients, even the laws of baking itself. By now locating the vast majority of this missing matter, we have performed a powerful validation of our core theories. We've confirmed that our model of the universe from the Big Bang to the present day is fundamentally sound. This isn't just a small victory, it's a resounding confirmation that we are on the right track in our quest to comprehend reality on the grandest of scales. This discovery also completely rewrites the story of how galaxies are born, live, and die. For a long time, our view of galaxy formation was relatively simplistic. Gas cools, falls into a dark matter halo, and forms stars. But the revelation that a huge portion of a galaxy's baryons exist outside its visible disk, in a massive, hot halo and the even larger cosmic web, forces us to see galaxies not as isolated entities but as dynamic nodes in a vast, interconnected system. The circumgalactic medium and the warm-hot intergalactic medium are not just storage lockers for spare parts. They are active, flowing components of a galactic ecosystem. This hot gas acts as a primary reservoir for future star formation. It's the galactic fuel tank, but it's also the destination for used fuel, the repository for material violently ejected by supernova and black holes. Understanding the precise balance between gas cooling and falling in versus gas being heated and blown out, a process known as baryon cycling, is the key to unlocking mysteries that have puzzled astronomers for years. Why do some galaxies form stars in a furious burst while others are quiet and dormant? Why do massive galaxies not have exponentially more stars than they do? The answers lie in the intricate feedback loops between a galaxy and its hidden atmosphere. The missing baryons were the hidden variable in this equation. Now that we are finding them, we can begin to model the true life cycle of a galaxy, from its infancy gorging on intergalactic gas to its mature state, carefully regulating its growth through powerful outflows that ultimately seed the cosmic web with the very material that will one day form new galaxies. Ultimately, this isn't just about looking back in time, it's about forecasting the ultimate fate of the cosmos. The distribution and state of all matter, both dark and normal, dictate the future of universal expansion. While dark energy is the dominant force driving that expansion, the gravitational pull of all matter, including the baryons we've just found, provides the counteracting tension. By finally accounting for the full amount of normal matter, we get a much clearer picture of the total density of the universe. This is a crucial parameter for determining the cosmos's final destiny. Will it expand forever, cooling into a dark, lifeless void, or could gravity someday halt and reverse the expansion? The precise inventory of baryons helps refine these cosmic predictions. Furthermore, the discovery that most ordinary matter exists as a diffuse, hot plasma has profound implications. It tells us that the vast majority of atoms will never again be part of a star, a planet, or a living being. They are destined to remain forever as part of this immense, hot intergalactic medium, slowly diffusing as the universe expands and cools. In solving the mystery of the missing baryons, we have not only completed our map of the present-day universe, but have also gained a deeper, more sobering insight into the long-term future of all ordinary matter, including the stardust that makes us who we are. Over the course of this investigation, we have followed an extraordinary trail of 25 clues, each one a testament to human ingenuity and our relentless drive to understand the cosmos. Our journey began not with a flashy discovery, but with a quiet, mathematical certainty from the cosmic microwave background, a primordial ledger that told us exactly how much normal matter the universe started with. This foundational clue set the stage for the entire mystery, revealing a staggering shortfall when we counted all the stars and gas we could see. From there, we ventured into the realm of theory, where the concept of the cosmic web and supercomputer simulations provided a revolutionary blueprint, predicting that the missing matter wasn't gone but woven into a vast, hot, and diffuse network, the warm-hot intergalactic medium. These simulations gave us a map showing us precisely where to look for this cosmic phantom. Armed with this theoretical roadmap, we then explored the diverse and ingenious observational techniques developed to catch a glimpse of the elusive Baryons. We saw how the Sunyaev-Zeldovich effect allowed us to detect the shadow of hot gas on the ancient light of the CMB, and how powerful X-ray observatories like Chandra and XMM Newton managed to capture the faint, intrinsic glow of million-degree plasma in the filaments connecting galaxy clusters. We decoded the cosmic barcodes imprinted on the ultraviolet light of quasars by the Far Ultraviolet Spectroscopic Explorer, finding the chemical fingerprints of highly ionized oxygen that placed the hot gas directly at the scene. We witnessed the power of statistical stacking, where thousands of faint signals were combined to reveal the pervasive whisper of the WHIM across the universe. And we marveled at the unexpected utility of fast radio bursts, whose dispersed radio waves act as a direct census taker for the free electrons strewn throughout intergalactic space. Further clues refined our search, from using pairs of quasars for tomographic mapping to understanding the critical role of galactic feedback and the massive, hot halos that surround galaxies. The Grand All-Sky Survey from eROSITA provided a panoramic heat map of the hot universe, allowing for a systematic inventory on a cosmic scale, while the precise measurements of baryon acoustic oscillations from the BOSS survey gave us an unshakable standard ruler to measure our progress against. Underpinning it all was the silent, gravitational architecture of dark matter, the master sculptor that carved out the cosmic web and dictated where the baryons would ultimately hide. Each clue, from the theoretical to the observational, has been a crucial piece of the puzzle, transforming a baffling, decades-long mystery into a solvable problem. We have progressed from knowing the matter was missing to understanding its form, its location, and its staggering abundance, now accounting for the vast majority of the universe's once lost atoms. This story is far more than a cosmic accounting exercise. It is a powerful demonstration of the scientific method in action. It shows how a persistent anomaly can drive decades of research, pushing technology and theory to their absolute limits. It reveals a universe that is far more intricate and interconnected than we ever imagined, where galaxies are not isolated islands but dynamic nodes in a continuous cycle of matter, breathing in and out within a vast, hot atmosphere. The solution to the missing Baryon problem validates our most fundamental models of cosmology, giving us confidence that we are on the right path to understanding the universe's birth, evolution, and ultimate fate. And the most exciting part is that this detective story is still being written. The final chapters are yet to come, and they will be penned by the next generation of astronomical giants now coming online. The James Webb Space Telescope and the ground-based Extremely Large Telescope, with their unprecedented sensitivity and resolution, are poised to study the cosmic web in exquisite detail. They will trace the dynamics of gas flow within filaments, observe the feedback processes from galaxies and black holes in real time, and may even capture the first direct images of the web's faintest structures. These observatories won't just find the last remaining percent of the missing baryons. They will transform the WHIM from a hidden reservoir into a well-characterized and understood component of the cosmic ecosystem. So, as we look up at the night sky, let's remember that the greatest wonders are often the ones we cannot see with our eyes alone. They are revealed through curiosity, through perseverance, and through the collective effort of countless minds dedicated to peeling back the layers of reality. The universe is still full of secrets, from the nature of dark matter and dark energy to the question of life itself. The mystery of the missing baryons shows us that no puzzle is too great when we combine imagination with rigorous inquiry. Stay curious, because the next great cosmic discovery is just over the horizon, waiting for the light of a new telescope to bring